Hello, good morning. Having introduced single step methods, I kept this title as analysis of single step methods, because if you look at the initial value problem y dash equal to f of x y with a given initial condition y of x 0 equal to x 0. So, what is y dash? You can think of that as a slope. So, now slope is equals to some function. Okay. So, we have to now find what is the corresponding y. So, this definitely needs some approximation. As you see in the Taylor series method, which we have discussed, we were using terms, various terms, okay, second term, third term, up to fourth term, fifth term, and then corresponding error, etc. So, that means definitely there is some approximation involved. So, can we formalize this approximation? So, that is the question. So, this needs some analysis, hence the title. Okay. So, let us recall Taylor series method. So, the Taylor series method, so this is Taylor series method. So, for example, if we stop at third, so then we write zeta n, where in this interval. Okay. So, now the question is, so the question is what happens if one uses more terms. So, the immediate answer is definitely the solution may vary. Yeah, of course, you are true, the solution may vary, but in what sense? Can we say concretely if we use more number of terms? So, with a general intuition, the solution would be better and things like that. Okay. So, we need to formalize this. Okay. So, we need to formalize this, and one intuition says number of terms control the error. So, maybe may. Okay. So, this maybe we can formalize, right. So, if you look at this, this is a first derivative, we have written it as this is nothing but y dash, second derivative and so on. So, that means after some stage you can take out, for example, you can take out a h, okay. But we need at least first approximation. So, suppose if we take out h, then these terms can be considered some function, okay, as some function, and the entire behavior may depend on this function. Okay. So, we have suppose if we introduce this notation for a particular h up to some terms, okay, then what kind of structure f may have, capital F. So, this depends on the number of terms, certainly, right. So, this depends on the number of terms. If this depends on number of terms, for sure we are approximating up to those many terms and started neglecting from this. So, what is this then? So, this is residual or error. So, what do you mean by this? If you compare with the exact solution up to this, then we are neglecting from here. So, that is called the residual or error, and we introduce this notation because the minimum is up to first, the minimum is up to first. So, as I mentioned earlier, you can pull out a h and express the rest as tau n plus 1. Okay. So, what is then tau n plus 1? So, this is local truncation error. Why? Because you are approximating up to some terms and you are truncating. Okay. So, therefore, this is local truncation error. Then we introduce a tau h, which is the max because at each interval, okay, if you consider 0 to 1, I mean n 1 to 2. So, we have the corresponding local truncation error involved. So, now we take the maximum and call it tau. So, this is global truncation error. Okay. So, now typically what kind of structure f would have? So, the structure f evaluate that. So, why this structure? Because we have pulled out a h. So, therefore, f starts from f of x n plus so on so forth. Okay. So, when we start our computation, so when we start our computation like this, so this would lead to say if we put down up to 3 terms, third term is like this and this is our okay, and this is called increment function. Okay. So, this is called our increment function because you keep on adding more terms. So, f behaves according to that. Okay. So, we have to formalize the error and also we have to formalize if you use 10 terms what is the behavior and what do you call the method. If you use 20 terms then So, this 10 terms, 20 terms, 40 terms. So, this number also has some significance, and same time whenever you have truncated up to something, then whatever you have thrown away. So, that also has a significance. Okay. So, we are trying to formalize, right. So, to this extent, how f behaves as h becomes small. Okay. So, this is our first term, then 1 or h over 2 we can pull out, then we have some remaining terms, right. So, therefore, so this would be plus plus, because the remaining will be of order h cube, right. So, this implies limit h goes to 0 tau n plus 1 h. So, this goes to 0. Okay. So, this goes to 0. So, this implies limit h goes to 0 tau h goes to 0. So, if this happens, then we say the single step method is consistent with the IVP. So, why this is happening? So, the way we have defined residual is h times tau n plus 1. So, therefore, tau n plus 1 goes to 0, okay, because at least one h remain in these. Okay. So, therefore, as h goes to 0, this goes to 0. So, if this happens, then we say the single step method is consistent with the IVP. Okay. So, up to what terms we consider, and then how do we formalize. So, we have to discuss, right. So, that is called order of a method. So, as your intuition says, the number of terms is related to the word order. Okay. So, a method is said to be of order p if for every x in A B the solution y x of the IVP satisfy the condition okay. So, a method is said to be of order p if for every x within this interval where the corresponding IVP is defined, the solution y x of the IVP satisfy the condition So, as h diminishes, your global truncation error is in big O of h power p. Okay. So, then we say the method is of order p. So, let us say for example, when we use first 3 terms of Taylor's method. So, what we would have h, then h square by 2 factorial, we have y double plus y 3 of zeta n, right. So, if we use first 3 terms, then fourth term you are not using, see 1, 2, 3. So, fourth term you are not using, right. That means, you started throwing it away. So, therefore, this would be h square by 6, because remember we have defined the epsilon n plus 1 as h times tau n plus 1. So, there is h. So, I pulled out one h. So, therefore, the coefficient is h square, and okay. So, if some place I made an equality, you may correct. So, we can have this range. So, therefore, tau h is max of mod. So, this behaves like this, because we can estimate. So, we can get a constant, and that together with 1 over 6 we can get some constant, and it behaves like this. So, this implies hence the method is, yes, you are right, hence the method is second order. Okay. So, this is one hand, because the number of terms and then how the error behaves, and when you consider 10 terms, 20 terms, what you call. So, that is nothing but it has a direct implication on order of the method. So, the next concern is if you consider up to 20 terms or 5 terms, whether really we are going to get solution that is close enough. Okay. So, which means convergence. Okay. So, let us formalize what is convergence. Convergence so, we have this approximation. Okay. Let this satisfy the scheme star in exact sense. Okay. Then the method is said to be convergent if okay. So, you can easily guess. So, method is said to be convergent if for every n. So, this is exact of the scheme, approximating scheme. Okay. So, then this y n is what we obtain. So, then a method is said to be convergent. So, when we obtain means you can see with the corresponding error into consideration. So, then a method is said to be convergent if the difference between the exact of the finite of the approximate scheme with the actual obtained after considering the error is less than or equals to C of h. When we say C of h, definitely this depends on h. So, now when do you say this is convergent? C h is an infinitesimal, that means this very small with respect to h. Okay. So, if this is going to happen, then we say the method is going to converge. So, what is the idea? So, you have approximated. So, what is the guarantee that this would really give you solution, okay, which that converges this scheme. That means, if you keep on computing and then if it blows up, then it is beyond our control, right. So, to reach the solution. So, when do you say such an approximation is convergent? You consider without error, okay, then consider with error, and the difference should be diminishing. Okay. It should be very infinitesimal, of course, depends on h. Okay. So, now correspondingly the number of terms also can be related. Okay. So, this is convergence. Further, the method is said to be convergent with order p if there exists a d greater than 0 such that okay. So, the method is said to be convergent with order p if there exists a d greater than 0 such that C of h behaves like this. So, for example, in the Taylor's up to 3 terms, d times h cube. So, where p is 2. So, this is convergent with the order 2. Okay. So, what is the motivation? How do we approximate? How many terms we consider? So, these are the quick questions one may come across. Okay. So, well, you have assumed that f is smooth, and then we try to expand assuming we have as many times as possible to differentiate. So, we proposed a Taylor series, right, but then we started compromising because we have to restrict within our discrete notation. So, when you have compromised, the questions are how many terms for this problem. Okay. And if I take this many terms, what happens? So, these are the questions, right. So, somebody would try to be little intelligent and then say, I would consider H pretty small. So small, I mean, I can start throwing from H square onwards, right. So, if you argue like this, yeah, definitely you get some approximation, right, because H square onwards you are just throwing. Well, definitely what should be your H such that your H square could be thrown, it matters. But however, if you assume that H square onwards you can throw, definitely you are going to get some approximation. Okay. So, let us look at it, what is that. So, this the title Euler method. So, what is the assumption? The assumption is step size h is very small, means order of h square can be neglected. Okay. So, now consider okay, because that is our assumption. So, this is nothing but y 1, y 0, because our IVP. Okay. So, now if we continue the next grid point, so we can formalize so this is approximation obviously. So, this is your Euler method. So, now so what is the corresponding error? The corresponding error we started throwing from this. So, now as we decided earlier, we can estimate this, and hence now if error behaves like this, then so that means Euler method is order 1. So, Euler method is a first order method. So, you can probably guess, because h is quite small. So, you started throwing from h square. So, it is a first order method. So, now definitely your solution, you are having a big compromise in some sense. Okay. So, we have to really think of better approximations. Okay. So, that is where we are going to formalize. So, better approximations. So, before we go, so because in order to go for better approximations, we should know what is the interpretation. Okay. So, geometric view of, so this would give a hint, okay, for our generalization. Okay. So, say we have this is x 0, x 1. So, now so this is general Euler method. If we write down at the initial point, and what is this? So, this is nothing but y dashed of x 0. So, what is exactly happening? Y dashed of x 0 has been approximated by this. Okay. So, use the tangent at x 0 y 0 as an approximation to the curve y x in this interval. So, that means, so we have say a function like this, then so this is y 0, so this is y 1. So, use the tangent at x 0 y 0 as an approximation to the curve y x in this interval, right. So, this is nothing but okay. So, according to this tangent, which is by okay, approximation to the function. Okay. So, this implies so this we call H. So, this would give us y of x 1 okay. So, this would give us, so that means you started x 0, x 1, x 2. So, we started approximating. So, next step if you approximate okay. So, then we have correspondingly this difference will be y of x 2 minus y of x 1 okay. So, we can march accordingly. So, then we get in a general sense okay, in a general sense we get this. So, this is the general idea. Okay. So, what exactly happening numerically? So, this is geometric. So, you consider y dashed of x equals to f of x y. So, then if you integrate in this range, we get okay. So, this is what now this has to be. So, we are having approximation of this in different patterns leading to various methods. So, that is what exactly happening. So, in Euler method, so this needs to be numerically integrated. Okay. So, this needs to be numerically integrated, right. So, suppose the simple situation is, say we go for is approximated by h times. Okay. So, this is called rectangular rule. Okay. So, g of x between x n to x n plus 1 you are approximating okay. So, you are approximating by the difference is h. So, h times g of x n. Okay. So, you are approximating by rectangular rule. Okay. So, if this is the case, then we get from here h times. Okay. So, this is Euler. So, now instead of rectangular, it can be generalized. Okay. So, how do we generalize? Say we generalize so, I will explain what is this. So, we are generalizing. So, not using simply a rectangular like this, you are giving some weightage see 1 minus theta at g of x n and theta at g of x n plus 1. So, restrict theta in this range. Okay. So, now this if we use it say so, this if we use it in A, so we get the corresponding approximation for f and then we may get different method. So, we get plus h remember this is at x n plus 1. So, with okay. So, this is more general right. So, if theta equal to 0 implies definitely Euler's method. Okay. Theta equal to 0. So, this is sometimes called implicit Euler method. Suppose theta equals to half. So, then both terms would survive, we get Okay. So, this is trapezium rule method. Okay. So, we discuss more geometrically. So, this is, and another observation, you see, to compute y n plus 1, right hand side is also demanding y n plus 1. Okay. So, this is then I am sorry, this Euler method theta equal to 0, this is explicit. So, this is not implicit, explicit, and this is implicit. So, now say theta equals to 1. So, this term goes away. Okay. So, we get y n plus h because theta 1 this goes away, this survives. So, this looks like Euler method, but this is implicit Euler method. Okay. So, now the idea is if you keep on changing, so then we are getting different approximations. Okay. So, we have to really generalize what are we doing. So, geometrically we started an interval, within an interval we try to approximate the slope with the corresponding function value at the initial point, okay, the beginning. If the interval is say x k plus 1, then y dash of x k we have approximated by the function value at x k, right. So, definitely this is giving only up to first order. So, then we started splitting it and giving 1 minus theta weightage to left and theta to the right, and then we try to estimate, and depending on the theta values we get various methods, right. So, what is the generality in this? It is nothing but approximating with various slopes, right. So, you can now think of how to generalize, that means we can approximate using 2, 3, 4, 5 slopes, etcetera, etcetera, right. So, let us see more carefully. So, this is generalization to single step methods. So, generalization of single step methods. H times some kind of average of slopes at intermediate points. So, this is nothing but so, now what is the idea? So, I put some kind of, so definitely the method would be different depending on what kind of average. Okay. So, what is the general idea? Approximate y dash of zeta n as a weighted average of slopes at intermediate points x n plus say x 0 plus n h. Okay. So, you have say x 0, x 1. So, we approximate, right. So, if you want to generalize this, so maybe this is x n, then this is x n plus a 2 h, then x n plus a 3 h, then somewhere we get x n plus 1, that means we have changed slightly. So, because within an interval x n to x n plus 1, we have introduced a notion a I h, where a 1 is 0, then a I equals to a I depends. So, it will be I equal to 2, 3 L. So, within an interval x n plus a 2 h, x n plus a 3 h, x n plus a L h. So, that means within an interval. So, first time if you recall, so this is y dashed of x n. Okay, we have approximated only using this slope at y dash of x n, but now within one interval slopes at several intermediate points, say in this case L slopes. Okay. Hope you are getting, this is the generalization, right. So, let us see a simple case in this, namely so modified Euler. So, this is x n, then you pick up x n plus h by 2. So, from where you are getting x n plus h by 2. So, this look at this notion. So, a I picked up as half. Okay. So, it is not equal. So, a I takes values depending on I. Okay. So, now a I, so here, so a 1 is 0. So, then a 2 is chosen as half. Okay. You can see. So, we are using midpoint. So, what are we step halfway across, then so this midpoint rule, step halfway across this, then evaluate f at midpoint, then use the corresponding slope to move further. So, which means y n plus 1 is y n plus h y dashed of x n plus h by 2. So, then this is nothing but f of x n plus h by 2 y n plus h by 2. So, this is equal to f of x n plus h by 2 y n plus h by 2 times. Okay. So, therefore, we get the method so this is modified if we use midpoint. Okay. So, now there is no necessity that we should use midpoint. Okay. So, let us say we step across x n plus 1 at x n plus k. Okay. So, then we get y dashed of n x n plus k. So, now it depends what kind of approximation we go for. Suppose somebody goes for an approximation x n plus h so we get suppose we go for so this is approximated by average at x n. So, at x n plus 1. So, then we get so this is approximated like this, then we get so this is your trapezoidal rule. Okay. So, now we are coming to the generalization. So, what is the generalization? Evaluate f of x y at several intermediate points within then take a linear combination of these values and add it to y n. So, you have seen how we have considered initially the weights 1 minus theta and theta. So, similarly, you are instead of considering only the end points, you can step across several intermediate points within a small interval x n to x n plus 1. Okay. I am not talking about Euler's method from x 0 to x 1, x 1 to x 2, x 2 to x 3 and then we got a generalized method. I am talking within an interval x n to x n plus 1, you go for several intermediate points. Okay. And then you start approximating those slopes and take a linear combination. So, that would give a better approximation. So, this is this generalization is leading to something called RK methods, which we discuss in the next lecture. Okay. Until then, bye.